Would you also be talking a little bit about the center you have there, Nanpeng, at the beginning?
Yeah, I'll very briefly touch upon that.
Thank you.
Center that we, yeah, sure, of course.
Darlene, should we start?
Yeah, I'd say go ahead. I think people just keep joining in as we go along.
Okay, sounds good. So I'll introduce Dr. Nanpeng Yu. Our presenter today is Dr. Nanpeng Yu from University of California, Riverside. Dr. Yu received his BS in Electrical Engineering from Tsinghua University, Beijing in 2006. Dr. Yu also received MS degrees in Electrical Engineering and Economics and PhD from Iowa State in 2010. Before joining University of California, Riverside, Dr. Yu was a senior power system planner and project manager at Southern California Edison from January 2011 to July 2014. Currently, he is an associate professor of electrical and computer engineering at the University of California, Riverside. Dr. Yu is the recipient of the Regents Faculty Fellowship and Regents Faculty Development Award from University of California. He received multiple Best Paper Awards from IEEE Power and Energy Society, Grand International Conference and Exposition Asia, and Second International Conference on Green Communication, Computing and Technologies. Dr. Yu also received 3 Best Paper Finalist Awards from IEEE Power and Energy Society General Meeting. Dr. Yu is the Director of Energy, Economics and Environment Research Center at UC Riverside. He is also a cooperating faculty member of the Department of Computer Science and Engineering and Department of Statistics. He currently serves as the Vice Chair of Distribution Systems Operation and Planning Subcommittee of IEEE Power and Energy Society and the Chair of IEEE Power and Energy Society Working Group of Data-Driven Modeling, Monitoring and Control for Power Distribution Networks. Dr. Yu currently serves as the Associate Editor for IEEE Transactions on Smart Grid, IEEE Transactions on Sustainable Energy, and IEEE Power Engineering. So let's welcome Dr. Yu today. Nanpeng, please take the lead. Thank you.
Thank you so much, Anamika, for your kind introduction and your invitation. So good morning, everyone. So today I'd like to talk to you about our recent work on machine learning for smart grid from pure data-driven to physics-informed methods. So first of all, I would like to acknowledge that this is not just my work. This is the work of our entire research team. So recently we started a new research center at University of California, Riverside. This is Energy, Economics, and Environment. We have over 50 faculties from 3 different schools that involves the ECE department, computer science department, Department of Statistics, Economics, Environmental Engineering. And we're basically working collaboratively on very large scale projects, such as how to solve the issue of wildfire or energy constraints. So the work is really done collaboratively with my postdocs who are brilliant, and all of my current PhD students and past PhD students. And before I get started, I also like to acknowledge all of our research sponsors, NSF, DOE, and national labs. And also in particular, we're collaborating organizations and funders. Those are many electric utilities who not only provided funding to us, but also more importantly, the extremely valuable large-scale real-world data set that we're able to explore on. So here is the outline of my presentation. First, I want to cover some of the interesting applications of machine learning in the smart grid area. I will first talk about the important applications for transmission systems and electricity market. And then I'm going to talk about the applications in the distribution systems and for end-use customers. Next, I will cover some key problems that were lab solved by deploying pure data-driven methods. In particular, I want to talk about the results that we get from a recently awarded DOE grant. And essentially, we're able to develop power system event detection and classification algorithms using extremely large-scale PMU data. And then I want to report on some exciting results we obtained for applying deep reinforcement learning-based control in power distribution systems. And next, I want to talk about some problems that we solved by developing physics-informed methods. Essentially, we're able to embed physics domain knowledge into the machine learning algorithms. And these applications include phase connectivity identification, electricity theft detection, and behind-the-meter solar PV generation estimation. I may not be able to go over all of these in detail, I might need to skip some material here. And finally, I will give you a few important takeaways that I think will be very important for graduate students and researchers in this domain of machine learning. So first, there are many important and useful applications of machine learning in transmission system. Researchers have been doing price and load forecasting for decades. And recently, a lot of researchers are developing algorithmic or machine learning-based trading strategies for virtual bids and FTRs in the electricity market. And it turns out that these algorithms could be extremely profitable, and that means the market efficiency is not as high as we thought. Other researchers have been developing wide area monitoring techniques using PMU data. You can also detect oscillation events with PMU data and use PMU data to validate the dynamic models. And of course, researchers in particular at WSU are well known for their linear state estimation techniques that you can do with the PMU data. And recently, many companies like EPG have demonstrated that you can detect event or equipment failure precursors with the PMU data so that you can take preventive or corrective action. And then a lot of researchers have worked on fault location using PMU data. And in the distribution systems, there's a lot more things that we can do. First, in addition to the typical forecasting, you can now do spatial temporal forecasting with the granular smart meter data. We have been exploiting the temporal correlation in the data for a very long time. Now with the smart meter data, we do observe very strong spatial correlations between customers nearby and the feeders nearby. The state estimation problem is a very important one for distribution network. Unfortunately, none of the electric utilities have a functioning state estimation in their distribution system. In other words, most of the operators are going blind when they're actually taking control actions on their system. Also, we don't have a very interactive and real-time visualization tool to see what's happening in the distribution network, which has millions of nodes. The topic of network topology and parameter identification is extremely important on distribution system. It's hard to imagine that the operator had been operating on a system without reliable topology and parameter information for a very long time. And we're going to show you how to do this with machine learning-based algorithms. Many researchers have explored customer behavior analysis by doing customer segmentation, non-intrusive load monitoring, figuring out the power consumption from HVACs, fridge, and so on and so forth. Other researchers have developed data-driven demand response algorithms to identify the demand response reduction potential from different customers. We have worked on equipment monitoring and predictive maintenance for distribution transformers. Here, the problem is a lot more challenging than transmission network because you can't afford to install a sensor or perform dissolved gas analysis on every single distribution transformer. Because for a utility with a few million customers, you may end up with over 1 million transformers, and it's too expensive to put a sensor on every single transformer. So we instead used low-cost sensors, smart meter data, voltage and power consumption, historical weather, and failure data to basically figure out the remaining health of these transformers. Later on, I'm going to be showing you how we are able to develop data-driven deep reinforcement learning algorithm to control distribution system where we don't have a very reliable model. And we're currently doing a pilot demonstration with original utility to make this happen in the real world. And finally, it's very important to perform anomaly detection. It's important to catch theft cases and even unauthorized solar interconnection. So next, I'm going to cover the first key problem that we solved with a pure data-driven method, which is system event detection and classification using the phasor measurement unit data. So let me briefly talk about the motivation. We all know that online event classification is crucial to enhancing the reliability of the system. If we can detect and classify events in a timely manner, then the system operator will have sufficient time to take corrective control actions. And as I mentioned before, we are very fortunate to be able to receive a $1 million grant and terabytes of real-world PMU data from all 3 interconnections from the United States. And with this data, we're able to develop an accurate deep neural network-based system event identification and classification algorithm. I'll briefly cover the key technical methods. So to deal with the high-dimensional PMU data input, we adopt the convolutional neural network as the baseline machine learning model. But we quickly discovered that using off-the-shelf machine learning algorithm, we cannot get too far in terms of improving accuracy. So for this particular project, actually, we are not given the network topology. So we do not know for sure where the PMUs are located. But when we're utilizing convolutional neural network, we notice that it has this parameter sharing scheme among the convolutional filters. So to make the parameter sharing more effective, we propose a graph signal processing based PMU sorting technique so that we can systematically arrange the hundreds of PMUs that we have in the input tensor to the neural network. And secondly, to improve the event classification accuracy, we propose an information loading based regularization technique to control the amount of information compression that we have in the deep neural networks. So here's the problem formulation. We're treating this problem as a classification problem where we're classifying the PMU data into the no event period, the line events, generator events, and oscillation events. Our input is a 3-dimensional tensor. The first dimension is time. The second dimension is the PMU ID. The third dimension is the PMU measurements, where we're able to calculate real power, reactive power, voltage magnitude, and frequency from the current and voltage sensors. So here's the overall framework. So we have 3 key modules. The first one is the convolutional neural network-based classifier. The second component, again, is the graph signal processing-based PMU sorting technique, which takes the incoming streaming PMU data and rearrange them in the input layer of the neural network. The third component is the information loading-based regularization, which further boosts the performance. So here are some details for the technical methods. Again, we're developing this graph signal processing-based PMU sorting technique because we don't know the exact location of the PMU, and we want to make the parameter sharing scheme more effective in the base convolutional neural network. Essentially, we're developing this graph signal processing-based sorting algorithm to systematically rearrange the PMUs in the input sensor. The key idea here is that we want to strategically place the PMUs with highly correlated measurements close to each other. And the detailed algorithms is as follows. So first, we will need to obtain the Pearson correlation coefficients between the PMU measurements. And then we can construct a weight matrix W and the corresponding Laplacian graph L based on those weight matrix, which is fueled by the Pearson correlations. And then we take the eigen decomposition of the graph Laplacian L. And finally, we can sort the PMUs according to the eigenvector corresponding to the second smallest eigenvalues of the graph Laplacian. Again, why this algorithm works, we have detailed proofs in our journal paper. So here's the results. Here are two heat maps that are representing each row and each column are representing different PMUs. The brighter the color, the higher the correlation. You can see before you sorted, the PMUs are placed randomly, but after you did the sorting, the highly correlated PMUs are grouped together. The second important technique that we developed within this framework is information loading-based regularization. This is really theoretical work that we have published in Transactions on Neural Networks and Learning System. So essentially, you can sort of think of an abstract representation of any deep neural network as long as it's used for classification purpose. Y is your labels, right? These are different types of events. In the real world, the Ys, the events, will be generating the input data X, which are the PMU measurements, based on some type of conditional distribution. And any deep neural network can be represented by this dashed two boxes. The first layer is multiple layers of the deep neural network. That's your encoder. You can have any layers you have, but you must have one last hidden layer of the neural network, and that's represented by Z. And then through that final layer, you're able to produce your class label estimation. So the main idea of information loading-based regularization is that this is a theory that helps us control the amount of information compression between the input layer of the neural network and the last hidden layer of the neural network. So the big idea is that we want to balance the memorization versus generalization. Okay, so as we know from information processing inequality, when you perform operations on data through different layers of the neural network, you're losing information. But how much information do you lose or compress really depends on the type of activation functions you have on the hyperparameters of the neural network, such as the number of neurons in the neural network and the number of layers. And really, depending on the entropy level of your input data, in other words, depending on the uncertainty level associated with your input data, we have two types of techniques that we can apply. Really, for low entropy data set where there's not a whole lot of uncertainty associated with your data, then we do not want to compress any information because we're not starting with a whole lot of information when we're training the neural network. And the horizontal axis is the mutual information between the input layer and the last hidden layer. The vertical axis is the mutual information between the input and output. Obviously, we want to maximize the mutual information between input and output. And the dashed line is if you have perfect world where you have infinite amount of data, this is how the mutual information between input and output will change in terms of input and last hidden layer. And the red one is theoretically what we can get with a limited amount of data. So again, with low entropy input, we don't want any compression. We want to push to the curve on the right. And the final training results will be somewhere between the red line and the blue line. However, the problem is that with high entropy input, such as PMU data, the red curve will be bending down. This is a theoretical curve. So to achieve a good results, we really need to compress the mutual information to a location where you can achieve a reasonable solution somewhere between the red curve and the blue curve. Specifically, how we're going to do this is that we're going to be augmenting the typical cross entropy loss function for the classifier with an additional term, which is the estimated mutual information between the input layer and the last hidden layer of the neural network. And essentially, you add this additional term. And unfortunately, the mutual information between the input and last hidden layer also needs to be estimated with another neural network. So the overall neural architecture is as shown here. The blue curve, the blue component is the typical classifier that you get off-the-shelf machine learning algorithm. We designed a mutual information estimation neural network that estimates the mutual information between X and Z. And we also have a bunch of parameters that needs to be fed. And once you feed this network and get the estimate between, you get the estimated mutual information between input and last hidden layer, you augment that, you add it to the typical cross entropy loss function of the neural network. And then you perform your typical stochastic gradient descent to update not only the parameters of the classifier, but also the mutual information estimator. Again, the details can be found in this journal paper below. So here are the numerical study results. We have 2 years of PMU data from Eastern Interconnect, over 1,000 event labels, which are provided by utilities and ISOs, almost 200 PMUs. We performed some data augmentation to get a 12-second subtensor sample. So that 12-second window is what we feed into the deep neural network in the online operations. We created a rather balanced data set in terms of non-event, line event, generator event, and oscillation events. So here is the performance on the validation data set. The vertical axis is the classification accuracy. The red curve is the baseline algorithm. The blue curve is the baseline algorithm plus the graph signal processing and information loading technique. As you can see, our proposed algorithm with these 2 additional techniques significantly boosted the classification accuracy. And the F1 scores on the testing data sets are shown in this table, where the bottom row shows the baseline deep neural network plus graph signal processing and information loading technique. We have a F1 score almost perfect, close to 1. But you can see that for the baseline events, it's struggling for detecting non-events, and it's having lots of trouble detecting oscillation events. And furthermore, we want to make sure that the deep neural network is not just a black box, it's learning something meaningful. So what we did is that we performed linear dimension reduction on the last hidden layer of the neural network, and we're plotting that here. We have 4 boxes with, this is an ablation study with different versions of the model. The top left is the baseline model. The bottom right is the most advanced version. You can see that in the baseline model, it's very difficult to differentiate different types of events for non-events. But if you have the most advanced machine learning model, you can easily separate events of different types. And furthermore, we explored the topic of transfer learning in this problem. The basic question we want to answer is that, can the events from the Eastern interconnection help us identify the events from the Western interconnect? The motivation is that although we have shown deep neural network-based event classification algorithm achieve very high accuracy, the downside is that they often require a large amount of event training labels and very long training time. But if a particular transmission grid operator only has limited event labels, then it will be very difficult to achieve very high event classification accuracy. And besides, training a neural network from scratch is very time consuming and resource consuming. So our main idea is that we want to accelerate the training of a model for a new transmission grid by exploiting the information from a previously trained model of a different transmission network. Again, the key question we want to answer is, does the neural network trained to identify the events for Eastern interconnection provide useful information and guidance when training the event identification engine for the Western interconnection? And the answer is a resounding yes. So the technique is fairly simple. So on this graph on top is what we did when we were training the deep neural network for the Eastern interconnection to classify the events. And once we train the encoder, remember we are using convolutional neural network, and they have convolutional filters which are sharing parameters. We are transferring those parameters to be used as the initial values of the classifier that we're training for the interconnection. And here are some numerical results. The top left figure is the results without transfer learning, and the bottom left is with transfer learning. Okay, and different color lines represent different amount of training labels. The blue curve represents only 1/8 of the available training data, and the red curve is the full amount of training data. So from these results, we see that transfer learning significantly reduces the required training time to reach a desirable event classification accuracy. And transfer learning does help shrink the uncertainty bounds with the early stage of training. And the comparative advantage of using transfer learning is more pronounced when a system operator only has a limited amount of training samples to start with. And again, this paper is under review at the conference. Okay, so next we're going to switch gears to distribution network. I'm going to show you how we can develop deep reinforcement learning based control for power distribution networks. So here's the motivation. We have been developing physical model-based control in power distribution system for decades. Okay, we have seen thousands of papers, but most of them do not get to be used in practice. Why is that? Although these physical model-based control have very good theoretical guarantees in control performance for ideal scenarios, they rely heavily on accurate knowledge of distribution grid topology and parameter. But if, like myself, if you get to talk to dozens of utilities across North America, you will know that none of them have reliable topology and parameter information. And that's why often you see unsatisfactory control performance. If you talk to your local utility, you get their smart meter data, you can see how often the smart meter data get beyond the typical plus minus 5% range. You have prevalent voltage violation. That's why that's what motivated us to develop reinforcement learning based or model-free approach to solve this problem. So RL or reinforcement learning based algorithms do not need reliable and complete network model. All we need is either real-time or historical operational data to learn or control policy. And furthermore, we can combine this with the existing control model, whichever the operator has been using. We can improve that existing controller's performance by learning its historical operational data. And of course, RL algorithm also have its own challenges. The first is how do you ensure the reinforcement learning agent is able to produce safe control policy. Sample efficiency is a big problem. This is not like a computer game where you can play the game millions of times and gather the data to train your model. We can only interact with the physical system for a limited number of times. It's very costly to interact with the real world system. So how do you learn a good control policy with only limited amount of data? The third one is the RL algorithms are notoriously unstable. So how do you ensure that the control policy you learned is robust? And finally, we're hoping that the controller is able to achieve a control policy that is close to optimal. Next, I briefly talk about the background for two control problems in the power distribution systems. The first is VOVAR control. Many of you are familiar with this, where the objective of the control is to maintain the voltages in allowable ranges. I can reduce network losses or minimize the equipment wear and tear. Researchers often do 2 timescale VOVAR control. At a slow timescale, you control voltage regulators and capacitor banks. And on a fast timescale, you control batteries and the energy set point of the smart inverters. And researchers have been developing centralized or decentralized control algorithm. And in the RL world, essentially that corresponds to a single agent RL algorithm and a multi-agent RL algorithm. The second problem that we look at is network reconfiguration. Again, the objectives is to reduce network losses and operating costs of switches and minimize the loss of load and increase the hosting capacity of DERs. You have static and dynamic distribution network reconfiguration. Static is for a single time snapshot. Dynamic is where you make sequential decisions over a operation horizon. And of course, wherever control you're doing, there must be some operational constraints. For example, you want to limit the voltage magnitude to be within 5% of the nominal value. For a radio feeder, you want to maintain the network radiality after you change the status of the switches. And there's other operational constraints that we can model. So I'm going to very briefly talk about a few of works to address the challenges of applying deep reinforcement learning technique for distribution system control. The first one I want to report on is experience augmentation. Remember, a major drawback of existing deep reinforcement learning algorithm is the poor sample efficiency. So the solution we come up with is that we can generate reliable synthetic operational experience data from the true historical data. So the key idea is as follows. We developed a Gaussian process-based model to learn the reward values, as well as the uncertainties associated with the synthetic operational experience. And when I say operational experience, I'm talking about network losses and voltage magnitude that you would have observed from taking a particular action. And our key idea is that we're going to be discarding the synthetically generated experience data that is highly uncertain, because most likely these contain large errors. And if you're training a model using erroneous data, you won't get a very good controller. So here I'm showing some results where you have different testing weeks, and on the vertical axis, you have the network losses that we're trying to feed. The black dot is the true results. The blue line is the Gaussian process model. You can see the blue line is tracking the black dots very closely. And on the bottom left, I'm showing not only the regression error of this machine learning model, which is represented by the orange lines, but also the standard deviation associated with the estimates. You can see that whenever the standard deviation is very high, you also have very high regression error. So that means our strategy of throwing away samples that have very high uncertainty is very effective in reducing. So basically, whenever you have high uncertainties, your regression errors are also very high. So the graph on the right is showing what's happening with the total operational costs in a testing week. The horizontal axis is the number of training iterations. The blue lines here is representing the baseline performance of deep reinforcement learning algorithm, DQN. And if you augment the historical operational data with our strategy, the results is recorded by the orange line. And if you're actually doubling the original training data with the true data augmentation, you actually achieve a similar level of performance with our proposed algorithm. So you can see that as training iteration goes on, the performance keeps improving with lower costs. And that means our strategy of creating the synthetic data set is very effective. The next work that I'm going to be highlighting is developing safe reinforcement learning algorithm and utilizing a special technique called ordinal encoding. Again, the motivation here is that the control actions taken by any reinforcement learning agent must satisfy some operational constraints. So our solution is that instead of formulating the sequential decision-making problem as a Markov decision process, we formulate it as a constrained Markov decision process. And basically that involves adding some constraints. Again, the details are in these two papers. So we aim to improve also the sample efficiency of the RL algorithm by two techniques. First, we want to develop a safe off-policy RL algorithm that is able to learn from historical operational data. The algorithm we created is called constrained soft actor critic. And we did it by synergistically combining the method of multiplier with the soft actor critic, which is a state-of-the-art reinforcement learning algorithm. Essentially, we must update the Lagrangian multiplier together with the parameters of the deep reinforcement learning algorithms. The second key technique we developed is that we're able to adopt an ordinal neural network structure to encode the natural ordering between the discrete actions of voltage regulating devices. Instead of going over the math, let me give you an example. So let's say you want to encode the turns ratios of the voltage regulator, which only have three tap positions, 0.99, 1.0, and 1.01. And instead of using the typical one-hot encoding for these three actions, we actually want to encode them with three vectors, 100, 110, and 111. And that means we introduce some inductive bias to say that the turns ratio of 1.0 and 1.01 has encodings closer to each other than the the difference between encoding of 0.99 and 1.01. And that turns out to accelerate the training process. The graph on the bottom left shows you the average weekly return. We want the performance to be higher. The blue curve is for proposed constrained software actor critic. The green curve is the state-of-the-art constrained policy optimization algorithm. So the CPO is developed by the Berkeley team. We developed the blue one. As you can see, we only need about a few thousand samples. In other words, half of year of training data. But the one developed by the Berkeley team will need almost 1 million data points, which is infeasible to gather in practice. Here, I'm also summarizing the performance of different RL algorithm or proposed one and the model-based control. As you can see, for the average weekly return, we're able to beat other models. For very large scale systems like 123, if you want to have a long control horizon, the model-based controller cannot even do that within 1 hour of time. And also the average voltage violation is 0 for a proposed algorithm, which means it is a safe control policy. The next difficulty we address is how do you work with limited amount of historical training data? Right? Not every utility can gather half a year of 1 year of historical operation data without significant distribution grid upgrade. So the motivation here is that it's very costly and time consuming to learn the optimal control policy by directly interacting with the physical network. And also learning from a finite amount of historical data set will lead to very large extrapolation errors. This is proved by the reinforcement learning literature. So the solution that we come up with is called batch constrained soft actor critic algorithm. So the key idea is that we're training a control policy to not only maximize the total discounted return, but also minimize the difference or the dissimilarity between the learned control policy and the behavior policy of the batch data. So the behavior policy is is basically the policy that the utility have been using to control their network. And this policy also generated batch training data. And we want our policy to be better, but also not too different from this baseline behavior policy. And the overall framework is shown on the right. In addition to the typical policy network and the state and state action value networks in reinforcement learning theory, we also need to build a generative network which approximates the existing control policy used by the distribution system operator. So the graph on the bottom left shows the performance of the algorithm. The green line is for batch constrained soft actor critic. As you can see, with the increase of training iterations, our algorithm is able to achieve lower weekly operational cost than the baseline RL algorithms. Again, the technical details and theory are shown in this paper in the link below. And finally, we were challenged by some reviewers to look into the area of multi-agent reinforcement learning. So how do you perform decentralized control in a system where each of the VOVAR controller is managed by a separate reinforcement learning agent? This problem is actually really challenging because each agent needs to learn 2 models. The first is a global state value function, which is shared, should be consistent among different agents. Also a local control policy, because each controller will have different control logics. Right? So the control goal here is that we want to, of course, maximize not only the local reward for each of the agent, but also minimize the difference in the state value functions. And that means the controllers needs to be able to communicate with each other. But knowing that we often only have limited communication bandwidth, it's infeasible for the agents to share the millions of parameters of their deep neural network in the RL algorithm. What we come up with is a communication efficient consensus scheme where the agent only share certain samples of the state value function. And in that way, the agent is actually able to quickly learn from each other and reach a consensus. So the graph on the top right shows you the hourly reward with different training iterations. And the blue line is what a centralized algorithm with global information is able to learn. The green curve is what consensus multi-agent RL algorithm. It's approximating the performance of a centralized controller. And if you're trying to reach consensus using ADMM method, your efficiency will be much, much lower. So essentially, our algorithm is very sample efficient. And because it's decentralized, we have shown through simulation study that the algorithm is very resilient against either a single agent failure, equipment failure, or even the communication link failure. Again, the detailed results are shown in this paper below. Okay, so now we're gonna switch gears. We have been talking about pure data-driven methods to solve important system problems. And now we're gonna show you how to solve another set of problems with physics-informed machine learning methods, where we're able to embed a physical knowledge into the machine learning algorithm. The first problem we're gonna try to solve is topology identification, in particular, phase connectivity identification. So the task is to identify the phase connection of each smart meter or transformer in a distribution network. So typically in the real world, a substation serves a few feeders, and you have 3 phase lines, and transformer's high voltage side is connected to different phase connections. One wire, that will be ABC. If it's connected 2 wires, it will be AB, BC, and CA. Our task is to identify which phase connection the transformers have. And we talked to dozens of utilities in the US. Very few of them have completely accurate phase connectivity information. And this is very important because without it, you couldn't even do load flow, let alone other advanced distribution applications. We spent 5 years on this problem. In the first generation, we developed unsupervised machine learning algorithm. Essentially, we take 1 month of hourly voltage data from all the smart meters, and we perform dimension reduction and central clustering. And that's the results shown on the graph on your left. So each circle represents a particular customer. The color represents different phase connection. As you can see, even with simple techniques on a simple circuit with only 3 phase to neutral connections, the algorithm can easily separate customers with different phase connections to different regions. Of course, we realized later on with harder circuits and higher number of phase connections, we have to do nonlinear dimension reduction and density-based clustering. And with the collaboration of Pacific Gas and Electric, they wanted to know if we further increase the granularity of the smart meter readings from 1 hour per measurement to 5 minutes per measurement, can the accuracy be further improved? And of course, the result is yes. And we also included some physical domain knowledge here by including some masking constraints that is able to further improve the results. And we created also a tool for the utilities to visualize the phase connection results on a typical feeder. And some other utility come back to us to say, can you further improve the accuracy of your algorithm? The answer is yes, but they have to do some field measurements. Essentially, we're able to use supervised machine learning algorithm to address the same problem. So utility have to send some crews to the field to measure the phase connection for a subset of the transformers. So the results are shown here. On the horizontal axis, you have the training data percentage from 5% to 95%. And the vertical axis is the phase identification accuracy. As you can see, for simple circuits, among the off-the-shelf machine learning algorithms, neural network with dropout layers perform the best. However, when we apply the same technique on harder circuits with higher number of phase connections, the accuracy are not as high. For example, for these 5 circuits that we have studied in the real world, the neural network doesn't produce very good results. And we realized actually, since we're using the voltage magnitude data in the distribution network, and the voltage magnitude doesn't deviate from 1 too much, so that means the entropy of the feature space is actually very low. So therefore, we can utilize the same information loading theory that we developed by adding this anti-regularization term. Essentially, we're not starting from a whole lot of data, so we have to decompress the information by penalizing any information compression. And by adopting this information loading technique and a advanced version of training data selection technique, we're able to significantly improve the phase identification accuracy on these 5 circuits. But that's still not good enough for many utilities. And that's what motivated us to develop this physics-informed machine learning algorithm, which basically allows us to develop a physical model that links the phase connection to the voltage magnitude and power injections through the three-phase power flow manifolds. And that allows us to formulate this problem rigorously as a maximum likelihood estimation and then a maximum marginal likelihood estimation problem. So we're able to derive the likelihood of observing the voltage magnitude given the phase connection and real and reactive power injections. And we're able to prove rigorously in the paper below that the correct phase connection achieves the highest likelihood values. And of course, it's still a difficult task to solve this problem, but we come up with a cute algorithm to solve this problem. And we validated results using real-world smart meter data, but we put this data on the typical IEEE systems. So with about 3 months of the data, smart meter data, we're able to achieve almost 100% accuracy. So here's the summary of the algorithm. The important thing is the bottom row, the accuracy. If you further improve your training labels and add physical domain knowledge, you're able to significantly improve your phase connectivity identification problem. And then I have 2 more topics that I will very quickly cover. The first is theft detection. So we all know what is electricity theft. You can either physically bypass the smart meter to steal power, or you can hack into meters or communication network. It's a very important topic. The world loses billions of dollars from theft. And unfortunately, none of the US utility, again, have a solid idea about how much theft is happening. So here is the high-level idea of our physics-informed data-driven method to detect theft. Again, we're utilizing the linearized model between power and voltage magnitude for each of the distribution secondary. So we find a tangent plane to this power flow manifold, and we establish some exploitable relationship between the theft data and honest data. So the key idea is that we're going to be utilizing your neighbor's voltage data and the sum of the power consumption in the secondary feeder to estimate a particular customer's real power consumption. And if there's a large negative deviation between the measured power consumption and the estimated one, that means there could be theft. And we developed some theory to provide theoretical guarantee to the negative residuals for the customer that are stealing power. So basically, these theories show that a thief's real power consumption residuals will become negative once the customer starts to steal power. And the other customer's residual must be positive to balance the sum to 0. Again, we're using real-world data from a 12 kV circuit from Southern California Edison with 6 months of data from 980 customers, 190 transformers. We're able to show that we're able to accurately estimate the power consumption for a customer by only using voltage data. And the anomaly score for a customer who is stealing power will be the highest among all customers on the feeder. And if the customer starts to steal more power, the anomaly score will be higher. And even the customer is stealing more than 0.3 kilowatt hour of energy, we can easily catch the customer. And the very last topic, I will just use 2 minutes to go over it. This is the problem of estimating behind the meter solar generation. We all know that many utilities are using net metering. That means they can only measure the difference between load and solar generation. But in many cases, we do need an accurate estimation of solar generation. So the key idea is in this diagram. So we basically iteratively estimate the technical parameters of a solar PV system and statistical parameters of a load model. So you iteratively estimate those 2 parameters from a physical model and statistical model. So the solar PV generation model is the physical one. The load model is the statistical one, where we're using the hidden Markov model. And the results is much better than the state-of-the-art algorithms. And furthermore, we can show that we can develop an enhanced version, which is able to estimate the behind-meter solar generation for a whole community of customers by jointly modeling the load of this group of customers with a mixed hidden Markov model. Of course, the model is not easy to estimate, but we have a unique algorithm to do the estimation. So here are some numerical results on some open source data set from Austin, Texas, where the bottom graph is the solar PV generation. The blue curve is the actual, and the green one is this more advanced algorithm. The purple one is the previous algorithm that I've shown on the previous slide, and the red curve is the state-of-the-art algorithm from the literature. Again, all the technical details can be found in this paper below, but essentially the key idea here is we're able to embed the physical model of the solar PV generation model into this machine learning framework. Finally, some key takeaway. So, please work with real-world data. We have found that the simulation data does not possess the same property as real-world data. And many algorithms developed with simulation data fail to solve real-world problems. So it's very important to get those real-world data and work on those. The second one is it's also very important to be able to closely collaborate with various utilities and learn about their current practice and some realistic challenges. And that allows you to develop solutions that could address real-world problems instead of simply writing another paper in the field. And finally, the most important takeaway is that it's very important to be able to synergistically combine your machine learning model with the physical domain knowledge. What physics can you incorporate? I've shown how you can incorporate powerful models or solar generation models. Other researchers are trying to incorporate ordinal differential equations from system dynamics into neural networks. I didn't have time to show this, but we developed graphical learning-based parameter estimation algorithm, so you're able to embed or encode the topology of the network into your machine learning algorithm. And finally, there are many useful statistical properties of the data generated from a physical network system. For example, many researchers have been using the low rank property or the spatial sparsity property of the data from PMU data or smart meter data to improve the performance. As I mentioned, the entropy of the data set is very important. Sometimes you work with, say, smart meter data, voltage magnitude, that's low entropy. But if you work with PMU data or image data, that's very high entropy. So the amount of information compression that you need to do to achieve the optimal accuracy is very different. And finally, there are unique spatial temporal correlations in the data from, say, SCADA data or PMU data that should be utilized when you're developing these machine learning algorithms. So that's it for my talk. I'm sorry I covered too much material. So hopefully, if you're interested in a particular area, just check out the paper and feel free to email me if you have any questions. Thank you.
Thank you, Nanpeng. Very interesting presentation with a lot of applications. I think we have 3 to 4 minutes for some questions. A couple of questions I saw have already been answered on the chat. Let me ask the latest one. So one question is for the split phase customer model used for energy threat protection, were both 120 and 240 volt level were metered?
Yes. So for the theft detection or the face identification, we assume that we have a mix of smart meters that some of them measure face to neutral and some of them measure face-to-face connections. And this is a common phenomena, I guess, for certain utilities. They have a mix of face to neutral and face-to-face connection. The difference is that in the measurement function, these two connections have a very small difference.
So I guess the next question is, can you please comment on the importance of behind-the-meter solar disaggregation for distribution system operators for distribution system monitoring functions?
Right. So, for example, one of the lessons I learned from talking to a utility why this problem is important is, for example, you need to perform, say, black start or load transfer on a particular feeder. If you do not know the exact amount of solar generation from certain customers, let's say you cut off power to a feeder that has solar, and the solar panel may take a certain time to start back up again. If you don't know the amount of solar generation before you trip the power, then you don't know how much load you're actually transferring to another feeder. So being able to estimate the amount of solar generation for these customers is very important for applications like load transfer and other things, like I was mentioning here, such as hosting capacity analysis.
Thank you. Any other questions from the audience? Okay. If not, let me ask one question. So, Nanpeng, what do you think are the main challenges of getting some of these machine learning, algorithms and methods in actual utility operational environment? What do you think are the roadblocks in your.
Right. I think one thing, I guess, I just wanted to talk from my perspective. For folks in academia, like researchers, we have to develop these applications using, I guess, similar platforms. So, for example, when utilities are using cloud storage for data, ideally you want to work with them and develop your code on that particular platform, so it's much easier for them to transfer that code to their operation. But this is really multifaceted. So utility has to recognize the importance of data analytics. So for example, many of them are running their equipment to failure, and that's a common practice. Everyone thinks it's okay until PG&E did it and created all the wildfires that killed almost 100 people. And at that point, you do recognize that the old way of operating the grid is no longer possible under all those extreme weather events that we're experiencing. And the next thing is then after they recognize the importance, we have to develop all these high value use case and demonstrate to them using their own data. Because a lot of times we're showing with simulation data, they're not really buying it. But if you are able to closely work with them and use their field data, they trust the results a lot more. And finally, I guess for us educators, we need to help educate those industry professionals who may not be experts for data analytics, for machine learning, to learn about these and get comfortable with the technology. But I think many utilities we're working with, they're moving very rapidly in incorporating some of the at least basic machine learning algorithm into their operations. So I'm very confident that the field will take off very soon for the industry.
That is great to learn. Thank you so much, Nanpeng, for presenting and for talking to us today. We really appreciate your time. I think we are at the noon time mark. So I think we'll end up and hang up from here. We'll talk to you later. And yeah, students, feel free to reach out to Professor Yu if you have any questions and if you want to, learn more about any of the several works that he has discussed today. All right. Thank you, everyone. Yeah,
Thank you.
Thanks,
yeah. By the way, I shared the link to my talk on the chat. So
okay, excellent.
Anyone feel free to.
Yeah, thank you so much. Yep, I'll make sure that we share with the students. Thanks so much. Have a great day. Bye.
You too. Bye. Take care.